Good afternoon. I'm Andrew Murphy. I'm the chair of this session, Propulsion and Energy Session 2. It will be followed by Propulsion and Energy Session 3. As was previously discussed, we recommend you hang around. So right now we're going to go through SAFRAN and Rolls-Royce. Unfortunately, Fabian from MTU took ill yesterday, so he's not here. So we've replaced that with an ad hoc panel. Philippe Majolka from Airbus has kindly agreed to join us. I'm going to sit on that panel along with the presenters, and it's a little ad hoc. You'll have to hang in with us, but it should be an interesting variety of topics that we hadn't had time to prepare for. So that should always be fun. This afternoon, after this session, will be Pratt & Whitney. I'll be presenting GE, and then we have a representative from the US Department of Energy. A lot of discussion about SAF today. The Department of Energy will provide, I think, a very unique perspective on where aviation sits in the greater ecosystem and how we should be thinking about that as an industry. So I really recommend, if you can, hang around for the whole afternoon. Our first presenter is Delphine Dijoud. She's from SAFRAN, a very distinguished career, started in 2004 in the thermal group at SAFRAN. She is lucky enough to be leading the CFM RISE program from an engineering perspective, and so she brings a very interesting view for all of us to hear. So with that, I'll hand over to Delphine.
Thank you. So thank you, everyone, and I'm happy to start this engine manufacturer session. It would be a sort of Isabelle appetizer for all of us, but I will try to do my best to give you more details than what you had already in Frank's session, because for sure he advocated a lot and he gave some of the major fascinating challenges we have in front of us. So, just getting familiar with this, that should be right. Okay, so this week we have heard a lot about sustainability challenge, for sure. The next chapter will be fascinating for us. When I started 20 years ago, we were on partial retrofit of engines. 10 years ago on the LEAP, it was the engine retrofit on existing aircraft. And right now, we are getting prepared for a revolution for the sustainability. So for sure, this challenge is incredibly fascinating, but it's also complex, as we have also to accelerate on the innovation compared to the past developments. So SAFRAN teams are fully engaged, and with 75% of our R&D effort, self-funded R&D effort, dedicated to sustainability, and that's for sure to meet our ATAG commitment to be net zero by 2050. Maybe I'm too small compared to that. Okay, so our decarbonization commitments span the entire life cycle of our products, but for today we will focus on maybe the most exciting part with innovation on propulsion. And I want you to show that it's not only a far-off dream, especially that we are still fighting against the post-launch slump. So, but I would like to make sure that you see that it's already happening, and that it's getting more and more concrete. So, for sure, after 3 days in this room, you have all mastered the lasagna recipe that started with Karim Mokadem on Monday. And for the sustainability, SAFRAN version may differ a little bit in terms of mix of the different ingredients, but the concept is the same, and I won't go further on it. I would like just to emphasize on the critical synergies between the different levels that we need to activate. Frank had a short section on the SAF. For sure, half of the decarbonization effort is linked to the introduction of a sustainable aviation fuel. And this massive adoption of fuel has a triple challenge for us with the availability, the volume, and the cost. And for sure, the less fuel our future engines will burn, the easier it will be for the introduction of SAF. So this combination is crucial to achieving both sustainability and also affordability, and that's a subject that we discussed also a lot in the previous sessions. So decarbonization is for sure a goal that we need to tackle all together. And to meet the ambition on SAFRAN side, we are working as many others on 3 key pillars. First is to invent and develop the new generation of disruptive engine solution. Also to work on the transition to the use of sustainable aviation fuel. And last but not least, introducing hybrid electric technologies. So I won't go through SAF after this slide. We have a significant experience on SAF already on current products. We are working on it, on the compatibility, as Frank mentioned that. And but the question is not only to validate the current product to be compatible with whatever SAF it will be. It's also to take into account those requirements in the future of propulsion solutions. So, if we focus on propulsion, so at SAFRAN and CFM, as well as other engine manufacturers, reducing fuel burn and so reducing CO2 emission is part of our DNA, and it has an environmental impact, but also for sure an economical one. And for almost half a century, it will be exactly half a century in 13 days. CFM worked on it to improve our energy efficiency, and over the past 40 years, the development of the CFM56 and then the LEAP engines has resulted in a remarkable 40% reduction in fuel consumption. But that's not enough. And to achieve a net zero commitment, we have to accelerate our technology plan. And we need to innovate faster and smarter. And that's the new goal is to push the efficiency by another 20%, but that time in only 1 decade. So the challenge requires disruptive solutions. So back to the discussion about evolution and revolution, and to advance twice as fast. And I would like to show you in the coming slides that we are ready to rise to the challenge of making the right part of Frank's slide real. So I had the incredible privilege to be part of the RISE program adventure at the very beginning, since the very beginning. I was there in 2021 when the partnership between GE and SAFRAN was officially launched, and that marked the start of the official start of our mission to develop new technologies for the next generation narrow-body engines. So the ambitious target is to reach 20% fuel burn reduction compared to the LEAP engines, and even 80% reduction if we combine that to the SAF introduction that we discussed before. So the open fan architecture that Frank's already described is for us the most promising solution for it, for sure combined with HP core technologies and also advanced systems such as hybrid electrical technologies. So back in 2021, it was only a promise to pioneer disruptive engine technologies, but 3 years after, you will see that this path getting reality, and that we had already good progress to share with you. So, in terms of propulsive efficiency, I think that Frank had already explained very brilliantly the open fan concept, but let's revisit why we are exploring this open fan concept. So the main thrust in decarbonization is for the engine to boost the propulsive efficiency, meaning reducing the fuel consumption and emissions. So you increase the fan diameter beyond the limits of traditional ducted designs and explore unducted configurations to explore the fan pressure ratio that Frank mentioned earlier. So this graph shows you the performance evolution over time for traditional ducted turbofans compared to unducted ones. If we start with the ducted ones, over 50 years for sure, the ducted had steadily improved, and they are approaching their limits in terms of propulsive efficiency. On the other hand, the unducted solutions, like the open fan, has just beginning to climb a new S-curve, let's say, of potential. So the propulsive efficiency is typically measured by bypass ratio. So just as a reminder, it's the ratio of mass flow bypassing the core compared to the mass flow entering the core. So you have the LEAP bypass ratio around 11. You can imagine that advanced ducted would be around 15 to 16, where at the same time the open fan achieves to get up to a 70 bypass ratio. So that's where you see the major step, even a major leap in terms of propulsive efficiency. The concept of unducted engines is not new to a CFM family. We had previously, in the 80s, GE worked on the G36 program on counter-rotating rotor, and in this program, SAFRAN was participating, and more recently, in a clean sky environment, SAFRAN led the counter-rotating rotor grand demonstrator with the participation of GE AVIATION. But what is new, clearly, is the simplification of the architecture. We took all the learnings from the previous experience. We also heard the feedback from the airframers, and we now consider that bringing a simpler architecture and also make it possible to install that under the wing are key to make it a game changer. So, and that's not the only thing that we change compared to the counter-rotating open rotor. We have also a different context. There are some breakthrough in materials, for example, such as the composite fan blades that were not there in the 80s, and it's the same for advanced modeling and also supercomputing capabilities. All those new items allow us to go further in terms of design. So such a disruptive engine architecture requires closer integration with the aircraft manufacturers, for sure, than ever before. If we have strong and early partnerships with our customers, it helps us to fully optimize this installed performance of advanced architectures. So we are set to have a demonstration for ground test demo and flight test demo with Airbus on A380 flight test bench. So it was released in 2022. And in parallel, we also have advanced integration studies for future aircraft configuration, and we also test them in wind tunnel tests. So thanks to the Clean Aviation support, we are progressing through the Ophelia project. This project involves the engine demo preparation, also technology maturation, and even modeling capabilities, and all in a consortium of 26 major European partners. So the progress are getting exciting with more than 250 tests already performed. So in 3 years, that's great. And all those test results are feeding the correlation of advanced models And we are able to correlate and refine models, and we feed the preliminary design of the engine demo with all those tests. So we are getting ready for the first engine ground test. It's set to begin mid-decade, followed by flight tests shortly after. Getting some example of that. Let's see, yeah. Video is working. One of the key milestones we have achieved is the completion of the first wind tunnel test campaigns for the unducted front of this engine. The tests were called Eco Engine. They were carried out in Onera facilities in Modane. It's 1/5 scale SAFRAN demonstrator. 200 and more than 200 test hours were conducted across different design configurations, mostly to test aerodynamics and also early acoustics performances. Initially, we started with isolated demonstrator, meaning that we had no integration to the aircraft. And then, in collaboration with Airbus, we advanced to testing the first installed configuration last March with a pylon and an aircraft simulator to study the installation effect. Right now, we are fine-tuning the correlation of the models between the tests and the advanced models. And the idea is to optimize, based on that, the blade design for the first engine demonstrator in the preliminary design loop, and also to get ready for the next design iteration. Right now, the results are already very promising for this first design loop, providing valuable insights in terms of aerodynamics, acoustics, but also aero loads. It's key to make sure that we optimize the weight of this engine. At SAFRAN, we are preparing for the next wind tunnel test campaign, focusing this time on acoustics at the NW. More updates to come in the coming months. And just one thing is that on this slide and on the next one, the geometry is a defeatured one. So you won't see the current design of the demo. This one is the first one we used to calibrate our models. It's too sensitive to be shared at that time, but the other tested configurations are far more elaborated than what you can see on this slide. So as mentioned earlier, the pace of testing and developing in the ROLLS program has significantly accelerated over the last year, surpassing the 250 tests. We are transitioning from component level tests to module level tests, so meaning TRL4. We had, for example, you have a picture in the middle of the high-speed LPT test performed at SAFRAN Villaroche. The first one was supported by a Clean Sky 2 project, but we continue testing multiple configurations on the LPT on a different test vehicle to explore the design space and optimize the LPT aero design. In parallel, we also carried out full-scale fan bird ingestion and mechanical tests on the open fan blades and also on the OGVs. Still at Villaroche. You have no picture of it at that stage. But we are getting ready even for the next test campaign with a second design iteration, which is close to the engine demonstration design. In parallel, we made progress on SAFRAN side on the advanced modeling as well. You have some pictures of it, still with defeatured blades. But the pictures are still a good example of how we advanced in terms of modeling tools such as LBM versions, for sure also leveraging from supercomputing capabilities. So tools are really here to help us deeply understand this disruptive architecture and associated installation effects and the correlation between the tests and the models are key, are crucial to make sure that we also accelerate the robustness of future design to get ready for the next products. In terms of also, I forgot to mention the manufacturing aspect. It's even getting more concrete with real parts. So on this slide, you can see the different example of full-scale engine demo parts already manufactured. So on the left, you have a fan hub, so which is a large titanium forged part, a critical one. And the different holes are for the different blades. In the middle, you have an additive heat exchanger produced by SAFRAN Aero Booster. And on the right, you have a turbine rear frame prototype, which is also using additive manufacturing, and it's produced with a SAFRAN additive manufacturing campus. So that's also a good example that the technical progress is not only is also reflected in our people. We have all the sister companies from SAFRAN who are contributing, and we have more than 1,000 engineers already involved in the RISE program, directly working on it, 2,000 within CFM. So we are advancing step by step, pushing each technology, each module forwards toward the fuel-scale engine demonstration that are coming very soon. So we discussed a lot on propulsive efficiency. That's not the only levers that we are activating, as I mentioned on the 3 key pillars at the beginning. So in parallel with all this effort on the propulsion, we are also working intensively to unlock the hybridization potential. So engine hybridization and the interface with aircraft electrification to meet our fuel burn reduction. SAFRAN has already conducted several hybrid elec engine test campaigns. We started with scaled engines to prove concepts around engine operability, engine controls, and so on. And we recently moved to a Silvercrest R&T platform, so real engine, where we completed more than 300 hours of tests, exploring at the same time power extraction and power injection. And we are getting ready for the next demonstration, combining HP and LP power offtake and injection, and with technology fully integrated, fully embedded in the engine. The hybridization roadmap for SMR engines are really powered by the whole SAFRAN portfolio in terms of technology. Much of this portfolio are coming from other market segments. It's clearly led on our side by SAFRAN Electrical and Power. So if I can just list a few of these key technologies, you have for sure the permanent magnet generators selected for their efficiency and their compactness, and operating with a 800 volt network. We have the associated power electronics, we have the high voltage harnesses, and all the protection and distribution systems that is quite common with the effort on the US side, and Roman later on the G side will give you also some other example of CFM effort on the different demonstrators. So for the hybridization as well as for the propulsive efficiency, we are really advancing step by step, not only working on the technology themselves, but also on the integration to the engine, on the interface with the aircraft. And what is really key on this journey is to unlock the different technical challenges, but also to work on the value of such a hybrid system in terms of, for sure, of fuel burn, in terms of operations, in terms of maintenance. We listed many of them in the previous session. So just to conclude on it, at SAFRAN, for sure, we are fully committed to achieving this target of net zero by 2050 for the commercial aviation. We get an ambitious roadmap to get there with a revolutionary side of the propulsion slide. We have a decisive contribution to drive this transition, but for sure we need to recognize that this challenge requires a systemic approach. We had an Olympic summer, so if I can use a sport image, sustainability is a team sport, and we will only cross the finish line if we work together across the industry, but also across the public sector, the academic sector, and that we pull also multiple levers, each contributing to the final solution. So, given the scale and the complexity of the questions we have on the table, we recognize that, and we are not pretending that we have all the answers to those questions, and we need to remain humble, to keep exploring, to keep learning, pushing boundaries with every test, with every design tweak to make it happen. But for sure, for me, that's the best time ever for engineers, young and less young ones, to imagine and to shape the future of the propulsion. That's it for me. Thank you.
We're actually back on track, but if anybody has a quick question, well, maybe Philippe and
we'll have time after that anyway.
Yeah, but if anybody has a question while we set up for the next session. So anybody got a quick question in the audience? Okay, so Alan and Philippe maybe will set up.
Hi, I'm Yojo Kita, Japan Aerospace Agency. Thank you very much for nice presentation. And I have one question about the containment issue, because, well, with conventional ducted fan, the case contain one's blade off, but there is no case with your unducted fan. But I noticed that your unducted fan is just right under the wing, but mounted a bit forward to the wing. Is that related to the blade of safety issue?
No, it's not only. For sure, that's the blade release is one of the challenge we have for certification also. That's something that we are working with our framers, because it's not only a question of installation of engine, it's not only a engine manufacturer choice. We are working on blade release, the debris itself, on the trajectories and so on. The location of the engine, it will be a compromise between this blade release, but mostly the aerodynamics aspects and aerodynamics and acoustics installation. So it's something that we are working. It's part of the cardinal challenges that we are working to make it happen. And I assume that I need to move there. And we will come back to that, I think, in the coming session.
Our next presenter, I'm not sure really needs to be introduced, but Alan Newby from Rolls-Royce. He's got 35, almost 40 years experience, and is the Director of Technology, Research and Technology at Rolls-Royce, and he will be giving us a talk about Rolls-Royce's path to net zero, roadmap to net zero. Thank you very much.
Thanks, Andrew. Thanks for the introduction. I was pleased Delphine said that we needed a mix of young engineers and more experienced engineers as well in the future, so I fit that. Right, I'm going to give you an introduction to what we're doing. I think part of the objective of these sessions was to give you some real evidence, as you've already seen from Delphine, about what we're doing. I mean, we've been to these sessions many years, showing roadmaps, and what we're trying to do in the next 30 minutes is really show the progress that we've made on them. So you've seen roadmaps, you've seen 1 or 2 roadmaps. I thought I'd show you 13 roadmaps this time. And the reason for showing this, when we talk about net zero roadmap, you might think the industry has got one aligned vision of how it's going to achieve net zero. I mean, as you can see from that, the answer is quite the opposite. But in fact, you see a lot of the common factors in there. So the blue on there is technology, the yellow is operations, the darker green is bio-SAF, and the lighter green is PTL SAF, and then the red is hydrogen. And the other one that's worth noting in there are some, the purple bits there are kind of demand impact, that says in some scenarios that they think there will be a reduction in demand, either forced deliberately or through the fact that some of the technologies that you put in and some of the new fuels may drive cost up to a price where you actually start reducing demand. But as you can see, quite differing views on all of those, but nevertheless some very common ingredients. And I'll talk about what we're doing in there. Interestingly enough, I won't say too much about operations, but I was at an event last week with EasyJet, and as many people know, they do a lot of flying in Europe, a lot of routes right across the European continent. And they've done some modelling which says if they could fly their routes directly, they could probably save 10% of fuel tomorrow. And that doesn't necessarily, so yes, I know single European skies is difficult and it requires political will more than technical will, quite frankly. But nevertheless, there are things they are doing with descent profile optimization, things like that can do. So we shouldn't necessarily wait for the big bang answer of single European skies. I think it's incumbent on all of us, particularly the airlines and the operators, to do what we can to mitigate that one. Because to me, that doesn't need lots of technology. It's things we could be doing today if we just need to make it happen. I circled one in red there. That's it's the Mission Possible Partnership one. And I wanted to just focus on that one a little bit more, not to go through the detail, because as I say, you've probably seen enough of these to last you a lifetime over the course of the last few days. But what I did want to do is just pull out some of the individual items. In particular, down the bottom there, you can see that the green bars are the SAF ones. And I think, and the yellow and the red. The yellow is the power to liquids and the red is battery electric and hydrogen. And so I think the key to those is that when you project all the way forward about how aviation is going to meet its obligations in terms of getting to net zero, it's going to be heavily reliant on 2 things. One is getting its fair share of biomass, and I'll talk about that a bit more. And we've already talked about the challenges of SAF and so forth, but in the near term, biomass is what we're going to use. A lot of the flights that have already been done have been using HEFA. We need to, there are other pathways cleared now, and the challenge will be ramping up the volumes of those. And then beyond that, we're going to have to go to power to liquid, so synthetic fuel, and indeed looking at other fuels like hydrogen and electricity itself. And what that means is that there's going to be significant demand on renewable electricity, on green electricity. So we've got to keep signalling as an industry that we need to make sure that any plans that we have from a technology point of view are matched, if you like, with what the infrastructure is down with and what countries' energy policies are. Otherwise we'll find ourselves short of those fuels, which will bring us home on that partnership. And as I say, I've got a couple of charts later on where we'll talk about some of those future scenarios and what it means. So I put this chart, we constructed this chart probably 3 or 4 years ago, and actually we've not really changed our view. We've done significantly more work on each of these swim lanes, if you like, over the last 2-3 years, and formulated, where we think it'll go and where they won't. But actually, that's not really changed our view. So today we've got kerosene, which is this ubiquitous fuel which we can put in gas turbines and small engines of all sizes. It's just a drop-in fuel and we can use it. And clearly, SAF is an alternative to that. It gives us a drop-in potential without having to change the whole infrastructure or indeed the engine or the aircraft design. One thing we will do on that one, and we'll talk a bit more about it, electrification can take many forms. One, as Delphine talked about, and I will mention, is to start gaining advantage through the operation of the turbofan, through more electric operations and through hybridization of various degrees, micro and macro. And we know that will happen and it will come. We're developing the technology and you'll see more of that. Those are hard yards to some extent, probably single-digit improvements for big engines, but nevertheless, we will do that. And then if you look at, I'll call it whole-scale electric propulsion down the left-hand side. So we know it's possible. People are flying planes today. We've in fact captured the world speed record for electric flight. But again, based on the energy density of batteries, and I think when this first started, there was a view that there would be really big leaps in battery technology driven by the motor industry, by automotive, but also aerospace. And we're not really seeing those coming along. So I think our view hasn't really changed, that the use of electric propulsion or all electric propulsion would be to relatively small aeroplanes. And I think even now you can see some of the runners and riders have dropped as we've gone through that process. Clearly you can enhance that by adding hybridization, and there's a number of concepts out in the world today which combine batteries with some form of heat engine, be it a gas turbine or a reciprocating engine, and they will effectively act either as a range extender or in combination with an electric system to provide your distance increases, if you like, relative to pure electric. And again, we could see those going into the regional space. Frank and others talked about hydrogen fuel cells, and again, the challenge on those is not just the energy density, the kilowatts per kilogram, if you like, but it's also the heat management. Today, particularly with low temperature PEM, it's relatively low grade heat, so you need a lot of real estate for your heat management, which has got both a weight and a drag implication. Again, we've done that. We've run fuel cells through our energy business, and we think at the moment, based on the size, we're talking 1, 2, 3 kilowatts at the moment. In the near term, at least, that's only likely to incur into the regional space. So if you want to go beyond regional with novel fuels, we still think you're going to need a gas turbine. That could be in combination with a hybrid solution such as a fuel cell. But actually, as Frank mentioned himself, a gas turbine combusting hydrogen is a highly power dense, energy dense, efficient solution, and that will see, that will give that opportunity if we can get the infrastructure and prove some of those technologies. And so what that means is we conclude that for the foreseeable future, that the gas turbine will still play a key part in those markets where the majorities of the fuel is burnt, but also, therefore, where the CO2 is produced. The other thing I'll address in there, there's a green arrow there that says longer-term potential on hydrogen. There's a bit of a belief, I think, that hydrogen gas turbines, hydrogen combustion is only going to be suitable for short-range vehicles. And I think that's not the case. If you look at the fundamentals, we all know that hydrogen is a third of the mass of kerosene for the equivalent energy output. And therefore, if you look at long-range aircraft, by definition, that carries a lot more of its total weight is fuel. Therefore, you get a bigger saving from using hydrogen. So from a fundamental point of view, it works. The challenge is then how you accommodate that amount of volume, because clearly it's 4 times the volume. So that's the challenge. So it's not a fundamental physics problem. It becomes more of an aircraft design. There's nothing that says, no, I can never get beyond 2,000 nautical miles or 200 passengers. It's about a good aircraft design. So in good tradition of having 3 pillars on addressing the sustainability, these are ones that we look at from our work at Rolls-Royce. So the first one, the kind of standard phrase that we use here, the best fuel is the fuel you don't use. So we continue to focus very, very hard, not just on the efficiency of the flying fleet. For example, we continue to put improvements into today's Trent family. This isn't all about next generation engines. But we are, and I'll say a bit more about it in a moment, investing heavily in bringing to market the UltraFan, which really is our next generation engine for both wide body and narrow body, and that gives us a step change in fuel efficiency. We talked in the panel session earlier about SAF. SAF will play a key part in the decarbonisation of aviation in the near term, the mid-term, and probably some of the longer term as well. So it's important that we understand what that means, and it's important that we show compatibility at both engine and aircraft level, and of course that we've got the availability. And then the final one is looking at alternative energy solutions, and in that we've already talked about hybrid and hydrogen solutions. And we've been trying to basically say, what are the risks associated with either hydrogen or electrification? Just work down them and say, right, what do we do to mitigate them? Is it a technical challenge, or is it a policy and regulation challenge? And along the bottom there, they're kind of obvious, but we write them down just to make sure we don't forget. There is still more to come from the way we install the engine and the aircraft together. I mean, traditionally, we've kind of optimized them separately. As engines have got bigger relative to the aircraft, that's got more important. And I still think there's improvements to come from that. And equally, we've all seen the challenges of not having maintainability and reliability, so we need to keep focusing on the in-service support. And we put a lot of technology into that, particularly on wing repairs and so forth. And then manufacturing operations, making sure, when you're looking at narrow body volumes these days, you've got to have a reliable and robust supply chain. and the unit cost will always be a challenge, so you've got to make sure we have advanced manufacturing technology to allow us to produce at rate and get the unit costs down. So those are the kind of final pillars on that. I wanted to talk a bit about UltraFan. We've talked about kind of the RISE one. This is basically a high-tech engine with a ducted fan rather than an unducted fan. And what we've got in here, relative to the Trent, it's a major change in architecture. The Trent architecture is basically laid down in the days of the RB211 in the kind of late 60s, early 70s, and we've kind of evolved that architecture. We think to get that step change in performance that we require for both the customers but also the environment, then we need to change the architecture of the engine. So what we've gone here is gone to a geared configuration. I think you all fundamentally understand the reasons we've done that. And when you do that, it frees off the fan diameter. You can go to a much, much larger diameter fan, passing much more flow, lower pressure ratio, lower speeds, which gives you an inherent benefit in both noise and propulsive efficiency. As the fan gets bigger, then clearly it takes up a large proportion of the engine mass, therefore you need to use advanced materials to drive that down. We're driving in composite systems on both the blade and the case. You need a gearbox in there to decouple the speed of the LP turbine from the fan, and I'll say a bit more about that in the next one, but we've designed that. And we also need a high-tech core as well. Yes, the improvements come from propulsive efficiency, but we're also driving the core technology high through improvements in overall pressure ratio, but also in temperature as well. As you drive the temperatures higher, it means you need more novel materials in there, and hence we're looking at things like ceramic matrix composites to allow us to do that, and advanced manufacturing techniques for the single crystal turbine blades as well. So you can see there, this isn't just a kind of propulsive efficiency. There are a lot of technologies coming together in UltraFan. And the one thing we did when we laid down this architecture probably 10, 11 years ago, this is a new engine architecture. It's not a spot point, it's not a large engine, it's a bunch of technologies, it's a new architecture, and therefore it's scalable for either wide body or narrow body applications. We chose to do the demonstration at wide body size because we think that actually gives us greater number of challenges, particularly on the gearbox and the integration, but actually that fundamental architecture will be suitable for narrow body applications as well. And in fact, some of those high temperature technologies that I mentioned, we're also retrofitting in some of the Trent fleet to improve both performance and durability. So the UltraFan, if you like, is the end point. But what we've done a significant amount of testing over the years to de-risk those technologies. These are some of the kind of, I'll call it the major subsystem testing. Underpinning these is a whole load of rig testing, for example. You might imagine we've done compressor tests, we've done things on journal bearings, we've done turbine rig tests, aerodynamic ones. These are kind of where it all comes together at subsystem. So on composite fan, we're now on our 5th generation low-speed fan. We've done an awful lot of work on composites as well. We've done, the standard blade off, the trailing blade ingestion, those kind of things as well. So we're good confident in the composite fan. Power gearbox, clearly, when you jump to that architecture, it's the key component in the architecture. We built a brand new test facility in Dahlewitz, just outside Berlin, to test that. And we've run a series of programs where we've done all the power, the attitude, and the power testing at that. We've also even done tests where we cut the oil off to see what happens as part of that. So we're really confident. We've actually run up to over 60 megawatts with that machine. So we know it's a powerful machine. Advanced 3, that's the core. So whilst the UltraFan, it looks like it's a high bypass ratio architecture, it's also a new core technology. We ran a slave system with an XWB fan, a Trent XWB fan, and a Trent 1000 LP turbine to prove that core works, and we've done 2 builds of that as well. So again, that de-risks the core. Alexis is our lean burn system. We talked in the previous panel about the importance of emissions. The UltraFan delivers a 40% reduction in NOx. What you can see there is the culmination of significant amount of rig work, multi-sector work in various facilities around the world. That brings it together. We basically inserted that combustor in a Trent 1000 architecture and tested that, and we're going to flight test one more time before, probably early next year now, to demonstrate the ability of that lean burn system. HT3, that's the high temperature vehicle. This time it's the Trent XWB 97K, where we've taken some of these CMC components, the high temperature components, and run them in a representative environment in a Trent engine. Thanks to Boeing, we were able to test some of the short inlet design, because clearly, as these fan gets bigger, if you just use the same rules for designing the intake of the fan, the same kind of length to depth ratio or length to diameter ratio, then you end up with a very, very long intake, and clearly that has drag and weight implications. So what we've been doing, working with ourselves and both our airframe partners, and here's a test we did with Boeing, is looking at can we shorten those, and we learned an awful lot about intake and fan intake compatibility from that. And then on the far side, the high-speed turbine, manufactured by our colleagues and partners ITP in Spain. They've done a significant amount of work on that, ran it in a representative condition, and then all those things come together to make the thing in the middle, which is the ultrafan. That's what it looks like on the test bed. We had to build a new test bed. This is in Derby, brand new cathedral-sized test bed to run this thing. The demonstrator is over 140 inches, so it's a significant beast, and you can see there some of the things that we ran. We put it to test last year. We got a significant amount of running out of it. We've taken it off test now to analyse the data and take a look at some of the components in there. You can see we ran it to over 85,000 pounds of thrust, which is the same kind of class as the XWB for the A350-900. We also, one of the things we weren't able to do on the rig, for example, is do the full rated accelerations for the gearbox. So clearly that was one of the first tests we did on this thing. Does it all work together? We've got a lot of data, a lot of happy performance and analysts and thermal management engineers in Derby trailing through all this data now to make sure we understand what it's telling us. But we're certainly very encouraged with what we've seen from the testing so far, but lots more analysis to do. So that's the ultrafan, great success, and that's, you know, even relative to our XWB, which is the most fuel-efficient engine flying today, this gives you another 10% of fuel burn improvement and reduction in CO2, as well as the NOx, as well as the particulates, as well as a 35% reduction in noise. So it's a big step forward. And the testing doesn't put there. What we've got here really is a kind of roadmap of the developments we'll go further. So we'll continue to test the wide-body version, which is the one you've got there. We've got more vehicles in build. We've got more hardware on it, so we'll continue to progress that. You may have heard at Farnborough that we announced that we would also start evaluating a narrow-body size version of the ultrafan architecture. As part of one of the clean aviation programs in phase one, we have a program called Heaven running today, which is allowing us to look at some of those scale effects. We talked earlier about combustion, for example. What's the right style of combustion chamber for a smaller engine? Does the gearbox scale? What does the fan manufacturing system need to be? So we've been doing a whole lot of work looking at the scale effects, and we'll bring those together in a ground test of a narrow body size engine as well. And then likewise, the technology doesn't stop there. We will continue to develop other technologies. I've pulled one out there that we've all been talking about, hybridization, for example, but there will be others. And we won't necessarily use the ultrafan itself as a validation vehicle. We'll use other vehicles in the portfolio, beware one of the smaller business jet engines or indeed one of the big Trent engines. And then ultimately, we'll bring those together in a flight test, and that's what we're aiming for as one of our targets through clean aviation as well. So it continues, the program continues, much more to do from an ultrafan perspective. I wanted to talk the next bit about, okay, that's and I've called this beyond kerosene. So we've talked an awful lot about reducing the amount of kerosene we use. What do we do beyond that? And so there's a lot of words on this chat, but the fundamental message is that we've been doing some work with others, and I'm sure other people have done similar analysis, looking at what the world will look like going forward and what the availability and what the right sources of energy to use are. And there's a couple of graphs there on the right-hand side, which I've taken from the Fly Zero study, which was sponsored by the ATI in the UK a couple of years ago, which looked at various scenarios. It was kind of hydrogen-based, but we did look at them. And you can see, fundamentally, you can see the build-up of the fleet, where the grey on there is kerosene, the lighter blue is SAF, the darker blue is PTL SAF, and the green is hydrogen. And what your demand is really depends on when you think the technology will be available. So you can see the one at the above as a relatively, I guess it's a baseline scenario where we assume that hydrogen would start first in the regional environment and it wouldn't come into a narrow body application till about 2050. And you can see the green bar there building up relatively slowly. And I think that's consistent with some of the announcements we've seen from our FRM partners. The bottom chart there says, okay, if the next narrow body were to be hydrogen powered, you still have a regional first. What would that mean? So that would bring in a narrow body in, say, 2037 for the sake of this argument. And that would pull your hydrogen requirement up further. And actually, the other thing that we tend, because we've drawn roadmaps that finish in 2050, we tend to think that's where the world stops. Hopefully it wouldn't. Hopefully we've solved the environmental problems by then. And we need to start looking beyond that, because the right solution for 2050 may not be the same and the right solution for 2070. So that's why we've done this analysis. And the conclusions that we came to on that one, I think, kind of obvious, but we did the work to do it, that in the near term, particularly through to 2050, the solutions will be dominated by SAF. Hydrogen may play a part, but it'll be relatively small. That means we need to make sure that aviation gets its fair share of bio-SAF, but we also need to ramp up the production of PTL SAF as well. And that means, as I said earlier, that flows into the energy supply. We've got to make sure we flag that demand for green electricity, because that's going to be critical to delivering the SAF, because bio-SAF is finite in its capacity, and therefore we've got to start producing PTL SAF. By 2050, then, we think in most scenarios hydrogens could play a limited role, but if you look at the cost of producing it and the energy requirement, then it looks a more energy efficient solution beyond 2050. Therefore, we should still keep the research going on hydrogen, because although it might not be all the solution for 2050, some of the technology and indeed the infrastructure have a long lead time on them, and therefore you've got to start delivering them now. And I think, if you look at that last but one bullet there, the work we've done that says, yes, there's a cost of this energy transition, but actually 90% or more of the cost isn't in the aviation industry. Yes, we'll have to develop new airplanes and maybe even change the infrastructure around airports, but the majority of the cost comes in the energy supply and infrastructure area. That's where that cost is going to be. So we're heavily reliant on working in partnership with the energy industry to deliver those improvements. And as we said earlier, that we've also got to take into account in looking at this, not just CO2, but the non-CO2 effects. So turning first to SAF, we've done an awful lot of work in terms of testing SAF. We've run all the engines in the fleet on SAF. We've done, every production engine has now been shown to be 100% SAF compatible, so we've run that right across the patch on that one. We ran the Ultrafan at first on 100% SAF, and we've done various defence and civil engines on that one. The two I'll point out, the one is we talked a little bit earlier about the emissions controls program. We learnt an awful lot. This is a pitch from eCliff 3, and interestingly enough, you can see that the A350 in the front is not producing contrails, and the chase plane is, and that was one when it was running on SAF. So we've already shown through that analysis that the fuel, particularly the cleaner fuels with fewer aromatics in, has less propensity to form to perform ice particles, and therefore persistent contrails as well. And that gives us some clues as to kind of how and when we use SAF as we go forward, particularly when it's in limited supply. Transatlantic Challenge is basically, we worked with Virgin Atlantic, Boeing and others in partnership to take a Trent 1000 on a 787, fly it 100% SAF all the way from Heathrow to JFK, and then basically turned it around, refueled it with Jet A1 to fly back. So that does two things. One, it proves you can do a transatlantic flight on SAF, but also that it's fully compatible with today's kerosene, and you use that to fly back on. The reason I've put a small modular reactor in there is A, because it's one of our Rolls-Royce product lines. If you like, we are in the business of producing small modular reactors, and B, you are going to need a lot of them and a lot of energy to produce that synthetic fuel as well. So we, just making that note again, that energy policy is a key part of this. I wanted to talk a bit about hydrogen as well. So a lot of questions. I think when you start looking in detail at hydrogen, there's been a lot of interest in it. Some of the questions are technical, but some of them are more policy and regulation-wise. So, before diving into some experimental work, which I talked about, we did a lot of work looking at the kind of economics and the fundamental feasibility of hydrogen-powered aircraft. Now, we got to a point where we thought we could, with our aircraft partners, we can design an aircraft and we could get competitive economics compared with aircraft today, particularly as you fly forward, you look at the cost of kerosene, you look at the availability of energy and so forth. Can the technology challenges overcome? That's what we're doing, and I'll show what we're doing about that one. We talked earlier about certification and safety. We've been through all the kind of regs as they apply today from an EASA point of view and looked at how they would change for hydrogen. So again, it's going to be hard. There's no two ways about it, but it's just a matter of working through them. And as we said earlier, we've got to engage early with the certification authorities, be it EASA, FAA, and the CAA in our case, but make sure you have that early engagement. But again, we think there's an awful lot of work to be done, and it'll need an awful lot of rigorous work on that one. But there's nothing today that says you fundamentally can't, but there is work to do on that one. And then you get into more of the kind of infrastructure type questions. Is there enough green hydrogen around? And today that's a real challenge. One of the tests we did where we had to source it from an island off the north of Scotland, because that was the only place we could get to green hydrogen. And moreover, can we source it at a viable price? So there's a lot of work going on looking at cost per kilogram of hydrogen compared with other fuels going forward. If we're going to produce it, then we need people to start investing in the plant. And if you go down a PTL or a hydrogen route, you're going to need hydrogen anyway. So we've got to encourage that investment in hydrogen production, but it's got to start soon. And clearly that knocks on, as I said many times, into the electricity supply industry. And the other one is how quickly can we do it? We've got to move fast because there's a technology lead time and there's an awful lot of infrastructure lead time on that. And it's not clear, which is the pacing item at the moment. So for this to succeed, you've got to solve the technology items. There's a policy question. There's also a regulation one that we've got to address to make it succeed. So in terms of working through it, the kind of fundamental challenges we see, clearly there's an issue of the supply that I've talked about and getting it to the airport. Today we've got an infrastructure which is geared up to providing Jet A1 to an aircraft on the runway, on the taxi area and in the apron. And then if you look at the challenges across, there's a kind of off-engine one, how you store it, and Airbus and others are looking at that in terms of tank design, fuel supply systems. And then from our part on the engine, we've got to pump it, and I think that's not without its issues. I mean, we know people pump hydrogen in large volumes for rockets today, for space applications, but the life requirements, the pressure and flow requirements in aerospace are quite different from space, so there's not necessarily doesn't read directly across, so there's work to do to get a robust pump on that one. Then you've got to warm it up because it's still very, very cold before it goes into the engine, and then you've got to combust it. And those are the kind of ways that we're addressing the challenges associated with hydrogen. And we've done a lot of work, so we're not just saying, oh, these are all problems. We've done an awful lot of work trying to de-risk it. So, for example, on combustion, we've done a significant amount of testing. The first thing we did, we took an AE2100 engine, which is what you'd find in a Saab 2000, or very similar to the engine in a C-130 Hercules. We took that and we just ran it on hydrogen. We converted it. We made some small changes to the burners, and it ran fine. It started, it shut down, and it burned well. So we knew fundamentally we weren't, there was opportunity there. And then what we went into a very systematic way of evaluating the fuel injectors. So we went through a whole design of experiments activity to looking at a range of fuel injector designs, because we weren't quite sure what the critical features were when designing a fuel injector for hydrogen rather than kerosene, which is where all our experiential database comes from. So we did a load of those, and we put them in rigs, atmospheric rigs and intermediate pressure rigs to try and down select to a number of burners. And then what we got from that was we took them to, the FAN is a full annular testing. That's a fully representative rig. This one ran in Cologne at one of the DLR facilities, and that gives you representative pressures, temperatures and mass flow. So we actually took the combustion system out of one of our business jet engines, a Pearl, and put the new injectors in and ran the system, and we got great characterization, which is why I'm reasonably optimistic that we can address the NOx problems. So we get some of the stability, the transient behavior, as well as the NOx performance on that one. And then what we're doing now is just a final iteration on those, primarily to make sure that we've got the life in those injectors for the next engine test system. So again, good confidence that we can address the combustion. So through working that one, my answer earlier is that's informed by a significant amount of atmospheric, intermediate and high pressure testing that we think we can develop a solution. Now clearly, as the NOx rules change in the future, then we may need to look at more sophisticated combustor nozzle designs, but for the moment we think we've got a good solution. And then on the fuel system itself, we've done an awful lot of work looking at the pump. The picture there on the bottom left is our kind of Mark I pump. That's ice forming on the outside of it because it's very, very cold, as you would imagine. Lots and lots of challenges, too many to go through here in terms of the pumping system. And so that pump is too big, quite frankly, to go on engine. We've got to do more work in terms of the speed at which we drive it and the basic design to get it on a size that would fit on an engine, but we are working through that. And then finally, heat management. I talked about the complex heat management system you need for hydrogen. We're working through that, and we're going to we've done some manufacturing trials, but we've also done some work on engine as well, and that's one of the engines that we ran down there. And then final one, just to finish with, we're actually bringing that lot together. So the first engine there is the one I mentioned. This is the A2100 with a kind of strange shaped inlet on it that you can see there. That's where we just did the fundamentals. Can we design an engine that can burn hydrogen, and can we do it safely? But part of that is not just about the engine itself. It's about how we manage hydrogen as a gas and as a fuel that we've not really used before. The engine in the middle is what we call engine zero. That's an engine where essentially we've modified the hydromech and the thermal management system, because today, many of you know, fuel does two things. It burns, but it also does actuation, it does heat management. So we've split those two functions so that then you can basically substitute the combustion fuel from SAF to kerosene. and that's already passed off. And then the final part of the trip will be to take it outdoors. We plan to test it at Stennis in the US. That's a picture of Stennis, one of our team out there doing the groundbreaking. So we broke ground on that facility probably a couple of months ago, and that will where we'll finish the testing and do that testing in an outdoor one. So hopefully by then we at least start to answer that technology question in terms of de-risking it. That's all I plan to say for now. I think we've got a panel session, but I just wanted to show, we've got the improvements in efficiency, the SAF and the hydrogen. We're making real tangible progress across all of those. And at the end of the day, we've got to work in conjunction with the whole energy system to work out what's the best solution, not just for aerospace, but for the environment in general. Thank you.
I think we can all agree that these two presentations, very impressive amount of work going on in our industry. Philippe, can I ask you to join the panel again to fill in for Fabian? We have about 24 minutes, 25 minutes for questions. It's very difficult to see from up here, but I think we have people running mics. They may need to borrow some mics. So if you have questions, please raise your hand and get a mic to you. That's much easier. Okay, one question over here.
Hi, this is Yannick Fernandez from Clean Aviation. Thank you very much for your presentation. And my question is more for Alan and Philippe around the topic of contrails on hydrogen that we were discussing before. So it's great to learn, Alan, that you are planning to run a gaseous engine on ground. Are you planning or is foreseen to try to advance a bit more in contrails in this one-to-one representative testing and get this or any other engine into flight end of the decade, by the end of the decade maybe?
I just want to be sure to understand your question. You're mentioning this H2 burn testing of an engine. Huh? That's right, okay. Yeah, of course, it will start by H2 burn onto ground, but I will rely on my CFM colleagues to run this kind of thing, of course. And when we'll be making this flight test demonstration on F380, the engine will be installed, by the way, on the back end of the aircraft. It's not going to replace one of the existing engines, so it's going to be installed on a stub at the rear part of the aircraft. And the positioning is, let's say, as best as we can to avoid to have a mixing, I would say, of what's going to be exhausted by this engine with the other four engines, because you want to measure what's going to be happening on this engine particularly. And to answer your question, yes, there's going to be, I would say, a sniffing test or checking of what's getting out of the engine as much as we can, because it will be a quite dangerous test, as we've been performing on the cliff and to Volcan, where you need to have a chasing airplane. I should have said, by the way, that we had a lot of support from DLR doing that. They had their own flight test airplane and they had their particular instrumentation. And I don't know if it's going to be DLR, by the way, for this F380 test, but we have to do the same thing with a flight test pilot which is able to follow another airplane very closely. That starts to be dangerous.
Maybe just one word on what we are doing for the ground test. So right now we are working within CFM to make sure the engine fuel system, so that's the first step on the ground, to get ready when Airbus will need us.
Okay, next question.
And yes, sorry, just maybe to Alan also was my question. So I think Philippe was referring to a flight test of a CFM engine. Are you planning to do something similar in Rolls-Royce?
When we launched the hydrogen program, we always said we had an ambition to flight test it. At the moment, we haven't got a committed plan. I think to some extent, we'll get through the ground test. We'll understand if there's issues there. Like CFM colleagues, you can do a lot of development with the cryogenic fuel system without putting it on an engine and going flying. So we will, in parallel, we'll run a cryogenic fuel system. And then I think the decision, do we bring those together and do a flight test? To some extent, we'll be guided by the market. Is it the time to do that? Is the market calling for a hydrogen propulsion system now? So it's a big step to go from that. You know, we think if we can de-risk the fuel system, cryogenics on the ground, and we can understand that we can run an engine through its transient range on hydrogen, and then the decision about when we put those together will depend on when the need comes, I think, in the market.
Okay, next question. here.
Thank you for great presentations. Rich Moore from NASA Langley. You mentioned the varieties of SAF and the non-drop-in versus drop-in nature. Could you speak more specifically about zero aromatic SAF and what it will take to get the modern and legacy fleet lower than 8% aromatics in the current spec?
Yeah, I think the work that because some of the tests that we've done were actually with, the transatlantic fuel did have some aromatics, had 12% aromatics in, so we made sure that was a compatible fuel. But actually, a lot of the testing that we've done on our engines would have been 100% SAF, if you like, without the aromatics. And I think one of the things we want to do on that is just understand the effects on some of the components in particular. Does it, change? We've talked about seals and things. We haven't seen, on the testing that we've done, we haven't seen anything that gives us any degree of concern, but clearly those are, relatively limited time testing. So I think for us, I mentioned in the panel earlier about understanding the impact on emissions, but also I think we'd want to run, fuel pumps, fuel management systems, fuel metering units, that sort of thing, through some kind of maturity testing, just to make sure there's no other effects that we haven't seen so far.
Just wanting to confirm that the tests we've been performing with Rolls-Royce on Aycliffe, but also with SAFRAN and CFM on the Vulcan was using a SAF without aromatics and without sulfur. It was pure SAF. So it works, but it works for a couple of flights. Now the endurance and the time you are using it is another issue.
Okay, any other questions? Okay, if nobody has any questions, we can finish early. I just say thank you for wonderful presentations. I have to follow that this afternoon, so that should be tough. But thank you very much to our panelists.